Well, welcome to your last chapter in our Organic Chemistry 1 course. This is Mrs. Hanson. We're going to share some selected topics out of Chapter 13, focusing on ethers. Oh, and I'll mention a little bit of epoxides at the end of our last lesson, but that is the only part of the chapter we're going to be pulling out. In this video lesson, we'll be looking at the first section, introducing what ethers are, kind of definition of the functional group and how to recognize them. We'll practice nomenclature of ethers and practicing naming, and then comparing the structure and properties to ethers to other compounds, especially the alcohols and alkanes, and just take a look at their intermolecular attractions in order to predict just trends such as boiling points or melting points and so forth. There is a second video lesson in this chapter. We'll take a look at the preparation of ethers and reactions of ethers and rounding out our lessons. So a two video chapter looking at what are ethers and how do we name them, and then looking at some important chemical reactions related. So let's go ahead and get started with our first section. What are ethers? So let's focus here in defining an ether. An ether is a group, a functional group that includes an oxygen, but that oxygen has to be bonded to two other alkyl groups. Your general structure, ROR, notice that it is an sp3 hybridized bond on the oxygen. So it is tetrahedral for molecular geometry. Well, tetrahedral for its electron domain geometry. Of course, the molecular geometry itself would be bent, but with 4 electron domains. So you can clearly see it is a polar functional group. Now, just to stress what the R's can be, the alkyl group, when you hear that name alkyl, it refers to an alkane, typically missing one hydrogen, simply because that's the site of attachment. So you could see this as an oxygen bonded to, let's say, 2 methyl groups. That is, by definition, an ether, ROR. The R groups can be alkyl, which is an alkane minus that hydrogen. They could be aryl, which is the aryl group is derived from the aromatic hydrocarbons. So for perhaps a benzene ring, again, minus a hydrogen to serve as a site of attachment. Or they could be vinyl groups, which just are the alkenes, but they cannot be next to a carbon that is double bonded to an oxygen. So even though I see an oxygen in this structure and it's leading to 2 other carbons, I cannot be fooled because this carbon is double bonded to another oxygen, and that is no longer an ether, not an ether, but it happens to be a next functional group called an ester. An ester is a derivative of a carboxylic acid, that C double bond OH. If we remove the H and place it with an R, we come up with an ester. So one of the things we need to just recognize, the criteria for an ether, I do recognize an oxygen bonded to 2 other carbons, but that carbon cannot be directly related to a double bond oxygen. And that's an acyl group, and that is a different functional group. So as we begin exploring and just recognizing what ethers are, let's just look at some common examples. Ethers are widely common in many natural and synthetic compounds. Here are some, probably some familiar names. Here's the molecular structure of the active ingredient in Prozac, an antidepressant. And notice here we have an oxygen, and as it reaches out, it's bonded to 2 other carbons. So there is an ROR functional group. This is an aryl functional group, an aromatic compound, and this again would be the alkane. Here another is vitamin E, which we know to be a strong antioxidant. Here is the oxygen bonded to 2 other carbons that are not next to a carbonyl carbon, so that also meets the functional group requirement of an ether. And finally, here's a third one that might sound familiar, some morphine active ingredient used to treat severe pain, a pain reliever. Notice here the oxygen is attached to 2 other carbon as part of the compound structure. So just looking at some very familiar ethers that we find in many natural or synthetic compounds. ROR is that characteristic functional group we're looking for. Now, when we go to name ethers, really we have two different methods, and IUPAC allows for both methods to be absolutely correct. The first of these methods is using a common name, and we just really want to emphasize that this is for simple ethers made of small, non-complicated chains. Non-complicated would mean no chiral centers or just something that's very easy to name quickly. So for instance, if I look at an ether and I can quickly name the small substituent groups, a common name works quite well. We simply name each of the R groups, is it methane, ethane, propane, butane, and so forth, arrange them alphabetically, and end it with the word ether. So with this example, I notice that the ether linkage is the oxygen in red. To one side has a 2-carbon chain, and on the other side we have a 1-carbon chain. The prefix for a 2-carbon chain is ethyl. The prefix for the 1-carbon chain is methyl, and we just list those alphabetically: ethyl, methyl, ether. Those are 3 separate words. Easy enough, isn't it? Here we have a tert-butyl. So notice this is a 4-carbon chain with 3 methyl groups coming off of that center carbon. So we know that to be tert-butyl. And on the other side is a 1-carbon chain. When we alphabetize, we do not use the tert, but we go by butyl, then methyl, then the word ether. So notice these are just simply unsymmetrical ethers. List each substituent group either side of the oxygen in alphabetical order and let the reader know it's an ether by stating so at the end. If we have 2 identical groups, it's even easier to name with a common name. And notice again, these are just small, non-complicated ethers. Here I have an ethyl group to both sides of the oxygen. So again, that ether group, ROR. And since they're the same substituent, we just say that's diethyl ether. And if it's the same substituent in both directions here with a 3-carbon chain, that's simply dipropyl ether. So they can be symmetrical or they can be asymmetrical, and then we must use the alphabet to list those in order. So the first of 2 ways to name the ether is just common names. Simply assign the prefix based on the length of the carbon chain, alphabetize them, and put the word ether at the end. Now, if we have larger, more complicated ethers to name, there's a second systematic way of naming these, and that's by choosing the larger group to be the parent alkane. The longer carbon chain is what I mean by the larger group. So that becomes the parent chain. The smaller chain is then named as the alkoxy substituent. So for example, here we have a carbon chain here. Let's kind of get an idea of what we're looking at. Notice here, this is the, I'll just make this red because it's been red. This is the ether linkage. On one side, we have a 2-carbon chain. And on the other side of the oxygen, we can count that there's a 5-carbon chain. With the 5-carbon chain, we know that that, of course, is the longer chain, so that now the root word becomes pentane. This would become the parent name because it's the longer chain. And that means the 2-carbon chain becomes a substituent group. And we just put F and then the little ending here, oxy, to let you know that there's an ether linkage. We also need to let you know where the ethoxy linkage is, and that's at carbon 1 on that straight chain. So for example, what if, just to say, another situation, what if I had a carbon chain, that's kind of a lazy little, let me make that a little clearer, sorry. I'll make sharper edges. And let's say we had, a group coming up here. Just to kind of give an idea that the longest carbon chain may not put the group, the oxy group, at carbon 1, but it may indeed put it as a substituent at a different location. So again, here's the ether linkage. There are 2 carbons to the left side, so that is going to be a substituent called ethoxy. And then notice that it is at carbon 2 this time that the ethoxy is attached, and this time it's attached to a 6 carbon chain, so it would be 2-ethoxyhexane, and so forth. So this one might have been misleading because it was directly attached to carbon 1, but the substituent could be attached to any of the carbons in that longer parent chain. Let's take some examples and just work through them together. Take a moment and draw this on your notes, and we'll just practice both ways. So again, I recognize, and I'll just highlight this as an ether linkage. The ether tells me that there is a carbon attached to the oxygen in both directions. On one side, we have a methyl, and on the other side, if we name this as a common name, let's just make, because this could go either way. This is a simple enough little ether. We could have a common name and then a systematic name. The common name, and I'm just labeling each side of the oxygen. The Me stands for a methyl substituent group. And when we name this benzene as a substituent, it's called phenyl. Listing those in alphabetized order, no, it worked out for me. Methyl, phenyl, and then the last word, ether. So there's its common name. Just simply looking at each one of those, in alphabetical order, list the substituents. Well, we could have an IUPAC or a systematic name as well, in which we find the longest parent chain and name it as the parent. Well, in this case, the benzene ring is the longest carbon chain, so it becomes the parent name, and here we see benzene. That's going to be the last part of the structure's name. And then we're just told to name this as a methoxy substituent. So here I have methoxy benzene. And I don't need a number on that benzene ring. There are no other substituents, so we already assume that we know it's at carbon 1. So just kind of sharing that strategy again, a common name, we listed the substituents in alphabetical order and then put the word ether after it, methyl, phenyl, ether. The systematic name found the longest parent chain to be benzene, and then named the substituent methoxy for the 1 carbon attached to the oxygen. Methoxybenzene, all one word. How'd you do? This takes just a little practice. Let's try some more. We're just really doing some from your homework. Here's another one. Why don't you pause the video, draw the structure, and try to name that, and give yourself a chance to work through, and then when ready, come back and see how you did. Well, welcome back. By this time, you've had a chance to draw and maybe kind of have some thought process of how you want to tackle this. You notice my note here on the slide said, we're not going to be able to give it a common name simply because it's too complex. As soon as we see a chiral center and several substituents, we know there's no common name. We have to indicate the chirality. So again, we're going to tackle this by finding the longest carbon chain, which here I can see is the cyclopentane. So I realize that the root word is going to, the parent name here is going to be cyclopentane. And everything else just gets named as a substituent. This substituent is 2 carbons long, and so we know to call it ethoxy. Here, at this particular site, we have a dichloro. Now, what about numbering? In the last chapter, we mentioned that alcohols always get priority 1. And so if this were an alcohol, I know that the oxygen would be granted the number 1 position. But that's no longer true for the ether. We want to find a numbering system to make sure that all substituents have the lowest number possible. And so if I were to number 1, 2, 3, 4, 5 in this direction, we'd have a 1,1-dichloro, and then we would have a 3-ethoxy cyclopentane. And just to kind of clarify why that's better than having numbered 1, 2, 3, 4, 5, this would have given 3,3-dichloro, 1-ethoxy cyclopentane, just to finish that whole thing out. And the reason we're discounting this is because 331 is a higher numbering system than having 1,1-dichloro. So this is the one we're deciding to eliminate because our job is to make sure we have the lowest structure, the numbering possible. So we just named that as 1,1-dichloro 3-cyclopentane. There's one more consideration, and that's the chiral center. So again, just to remind ourselves, a chiral center is a carbon that has 4 unique substituents, and this indeed does. There is a hydrogen, not drawn, but we know that is there. We have a wedge out to an oxygen. We have a 2-carbon chain that leads to chlorines, and here is, again, a 2-carbon chain that leads to chlorines. So is that a chiral center? And yes, indeed, we can see it is a chiral center. There's 1 carbon leading to the chlorine. Here there's 2 carbons leading to the chlorine. So they are not the same length chain. Therefore, it's a chiral center. Okay, so that's clarified. Let's just kind of redraw to make this a little bit cleaner. We have a cyclopentane, and knowing that we have a oxygen and a couple of chlorines here, just to assign priorities. Of course, oxygen would be of highest priority. The carbon that is leading directly next to the carbon with 2 chlorines would be second priority. And the third priority would be the carbon that has a carbon before the 2 chlorines. So we have a priority here in twisting this direction, which is clockwise, which we know to be an R configuration. And no need to flip because the hydrogen is a dash. It's a behind. The lowest priority is in perfect situation to have this as an R center. So to kind of clarify, the last thing we need to do is to let you know that there's an R chiral center. And we'll just denote that right at the top of the name there. So putting that all together, just to kind of see that all worked out, we know that we had a chiral center. We decided it was spinning R. We used the parent name of cyclopentane. We choose the more complex group as the parent, always making sure to give the lowest number possible, deciding that 113 was lower than 133. And that's how we decided that the carbon with 2 chlorines had to be carbon 1. When we named that 1,1-dichloro 3-ethoxy cyclopentane. And the last thing we did was to consider the chirality and worked through together, noticing it was a clockwise spin. So the R configuration, dash 1,1-dichloro 3-ethoxy cyclopentane. These just take a little practice and you'll have them down. I'd like to do maybe one more, 2 more. We'll see how our time is going in the lesson. These are your homework, so the more that you like to just practice and come back to check, that's fine with me. We can have another opportunity to do an IUPAC name for each of the following compounds. This is very similar to one we just drew. We have a cyclohexane as the parent chain. The longest carbon chain is a cyclohexane. Here we have an interesting situation. How do we go about numbering this? If I start with number 1, 2, and I continue around, our numbering system would be 1-ethoxy. And then we would have a 2-methyl. And then we could see that as cyclohexane. Now, is that any more correct or less correct than saying if we had numbered 1, 2, 3, 4, 5, 6? My hand changes this color, so that's why you're seeing it change color. When I rest my hand on the screen, it changes colors. Sorry if that's distracting. If we had numbered in the opposite direction and made the methyl, we would end up writing, still alphabetical, 2-ethoxy, 1-methyl cyclohexane. Now, what is better is the fact that when we have an equal number of, we're not lowering the number 1-2, it's the same numbering system either direction, but what would then dominate is the alphabetical order. So there is one correct answer. You want to go by the alphabet. If there isn't an opportunity to lower the numbering system, make sure you put the lowest number with the lowest alphabet and priority. 2-ethyl, 2-ethoxy, 2-methyl cyclohexane, and that denotes this guy. Now, the last thing you want to check before you say done, are there any chiral centers? And if so, we've got to name them. And this is good review from chapter 5. I actually noticed that we have 2 chiral centers here. Can you find them? We want to find carbons that are attached to 4 unique groups to find the chiral centers. So I recognize that at carbon 1 is a chiral center, and again at carbon 2 is a chiral center. And you want to go through and make sure you can decide if they're spinning clockwise or counterclockwise, and when do I flip. So let's just work through this together. We'll do it carbon 1 first, carbon 1 being, of course, in the red numbering because we eliminated the choice that was green. Let me just get rid of those numbers. At carbon 1 is a chiral center, and at carbon 2 is a chiral center. Let's focus on carbon 1 first. Of highest priority would be the oxygen. The second highest priority would be the carbon that's attached to the most carbon. And then the third priority would be the carbon that's attached to the fewest carbon. And so we see ourselves spinning in a clockwise fashion. However, priority 1 is a dash, and it's supposed to be a wedge. So that tells us that we need to just flip the configuration so that we're reading this as counterclockwise, and we know that that is an S configuration. So at chiral center carbon 1, we have an S configuration. Let's do the same thing again, but for the second carbon, carbon number 2. Of highest priority would be the carbon that's attached to the carbon attached to the oxygen. So this will be top priority. The second priority would be the carbon that's attached to the more carbon. Then here's carbon attached to just hydrogens. So again, this is spinning in a counterclockwise fashion. The highest priority here from this carbon to this carbon is just a straight plane, so we do not need to flip. So this also comes out as the S configuration. So putting all that chiral stuff together, this is the final name. 1S, 2S, 1-ethoxy, 2-methyl cyclohexane. What I love about this is it's making us remember everything we've learned so far. It can really test you on nomenclature, but both in the alcohol and the ether groups with just these last 2 sections. And again, I just took a screenshot of all of the practices that you'll be asked to do. You can certainly take a moment and draw these on your paper, and I can just quickly share with you some strategies as you approach them. Pause the video and draw these last 3 structures on your paper, and just start up again once they're on your paper. Okay, welcome back. Let's take a peek at what is listed as letter B and just see how you did. Give yourself some feedback as you practiced naming. You wanted to find the longest parent chain, and on the longest parent chain, you found that to be a butane, that there was a 4-carbon chain. At carbon number 2, we had an ethoxy substituent group, 2 carbons in length. And we noticed that there was a chiral center involved at carbon number 2 as well. When you worked through the spin, it came out clockwise. So you put that together as R2-ethoxybutane. If you're ready to check the next, let's do it. Here was your next structure. You had a benzene ring and then 2 methoxy groups hanging off of that. So just naming that with a systematic name with 2 ether linkages. The parent, of course, is the longest chain, which would be benzene. 2 identical substituents, so we'll just say 1,2 dimethyloxybenzene. And there are no chiral centers to have to worry about here, so that's good. And when you're ready, let's just check the last one you had drawn. Give yourself feedback with this. With this particular structure, maybe I'll erase this and we can kind of talk through this together. You found the longest parent chain to be an alkene, and when you numbered, you found that to be a 5-carbon chain. At carbon number 2, you saw an ene, the double bond. So now I'm noticing the parent name will be 2-pentene. There were 2 substituents. One was this substituent known as ethoxy. And here, this is known as methyl. So at carbon 2, there was an ethoxy, and at carbon 3, there was a methyl group. So we needed to alphabetize the 2 substituents. Ethoxy comes before methyl in the alphabet. So as we're looking at 2-ethoxy, 3-methyl, 2-pentene, putting all those together. And the final thing, did you remember to consider stereochemistry? And that was the part where you had to decide, based on seeing a double bond, is this an E or a Z configuration? So that's where I just draw a line through the double bond and see what priority lies on either side of the double bond. The highest priority in this particular carbon would be the ethyl over the methyl. And on this side, let's just make sure we see this is of higher priority. More carbon is of higher priority, so ethyl over methyl. And on this side, this carbon, it has a methyl and then the ethoxy. So again, this is the priority, the leading to the oxygen, a more complicated substituent group. Now notice that the priorities are on opposite sides of the double bond. Therefore, opposite, which starts with an O, leads me to the E configuration. So the stereochemistry E, 2-ethoxy, 3-methyl, 2-pentene, putting it all together. I encourage you to just practice that nomenclature. It will appear on your exam, and it's a good way to just get all nomenclature reviewed in preparation for the final. And the last section, very brief topic about structure and properties of ethers. So I mentioned at the start that the functional group of an ether is very similar to that of water or an alcohol, being that it's an sp3 hybridized tetrahedral for electron domain. So notice that water they have listed as 105. I actually learned that as 104.5, but somewhere in that neighborhood for a bond angle. Methanol, which now replaces one of the hydrogens with a methyl group, again increases the bond angle. And if I add 2 methyl groups on either side of the oxygen, the bond angle increases it a little bit more. And this is just really just based on steric hindrance. you want to make sure that you're giving those methyl groups plenty of room to move away from one another. So you'll see the bond angle kind of increase as the more carbon around that oxygen increase. And what I notice here also is water, of course, meets the criteria for H bonding. It has an oxygen directly attached to a hydrogen. Alcohols meet the criteria for hydrogen bonding, but the ether groups does not. So in other words, because the oxygen is no longer attached to any hydrogens, we've actually decreased the intermolecular attractions between the molecules. So alcohol with alcohol, this is our OH group for an alcohol, you can see a very clear intermolecular attraction of your H bonding that creates a very strong intermolecular attraction, very sticky molecules. Therefore, it takes even greater amount of energy to force them to boil. High boiling points for alcohols. But if I compare that to an ether cannot set up. If I had an ether, let's say ROR, sitting next to another ether, ROR, there are no hydrogen bonds available from ether to ether. It can receive a hydrogen bond if I had an alcohol. If there is a hydrogen from a solvent, let's say, there can be an attraction between an alcohol and an ether, but there is nothing available for that same criteria for ethers together. So based on that, you just see boiling point trends. The alcohols have the highest boiling point of all because they have dispersion, dipole-dipole, and hydrogen bonds. By the time we get to an ether, we've eliminated hydrogen bonds, and by the time we get straight to an alkane, all we have left is dispersion. So they have very low boiling points, increased molecular attractions to an ether, and the highest of all, with all three intermolecular attractions, would be the ethanol. Notice that we mentioned ether is a polar molecule. There is an interesting component, electron density pulling rich toward the oxygen to create dipole-dipole interactions. It would not exist there in terms of straight chain propane. And keep in mind, because surface area plays a large role in dispersion forces, the larger you have, surface area for ethers, the higher the boiling point. So again, these just interactions, if I have a long carbon chain, these interactions between those carbon chains have an opportunity to set up more dispersion forces, more temporary induced dipoles, and the molecules become a little bit stickier. Remember also that the larger the ether, the heavier it is in terms of molar mass. And again, it just takes more energy to cause that to rumble and get to the boiling point, the heavier, longer chains. And that takes us to the end of our first lesson. In your next video, we'll talk about preparation and reactions of ethers.